It's a great pleasure to be here. Thank you so much for inviting me to give this talk at ScaledML. I'm also very honored to be a speaker among this distinguished list of speakers at ScaledML. My name is Keshav Pingali. I'm the CEO of Katana Graph. I'm also a professor in the computer science department at the University of Texas at Austin. And today I want to talk about knowledge graphs, graph AI, and the need for high-performance graph computing. Traditionally, high-performance computing has been associated with computational science applications. So typically you have a partial differential equation of some kind, you discretize it using finite differences or finite elements, and then when the dust settles, you end up with a large linear system, AX equals B, that you solve in parallel using some very big cluster, such as the supercomputing cluster that we have at the Texas Advanced Computing Center. But about 10 years ago, a group of colleagues and I realized that there was an opportunity to take all of the techniques that we have developed in high-performance computing and use them in a different domain that was emerging, and that is the domain of graph computing. So to understand what the opportunity is, to see why this is an interesting thing to do, I'm going to make the argument in two parts. One part of the argument has to do with the volume of data, and the other part of the argument has to do with time to insight. When it comes to the volume of data, all of us are familiar with these terms like data tsunami, data flood, data deluge. What all these apocalyptic terms mean is that the world has generated an enormous amount of data, and we're generating new data at an accelerating rate. And so if you go to sources like IDC 20, for example, you see numbers like by 2025, the world would have generated 175 zettabytes of data. More than half of the world's data has been created in the last 2 years, but less than 2% of it has been analyzed. Now, some of this data is relational data. You can represent it in the form of tables. You can process it, analyze it very effectively using SQL. But increasingly, more and more of the new data that's being generated is what we call unstructured data that doesn't quite fit the relational model very well. A lot of this unstructured data can be represented usefully using graphs and then processed using graph algorithms. And so that's one part of the argument for why we need high-performance graph computing, the sheer volume of data that's being generated, a lot of which can be represented using graphs. The second part of the argument has to do with time to insight. In most application areas, you have a window of opportunity, and if you can do your analysis and get insights within that window of opportunity, then you can profit from it. But if your insights come after that window of opportunity has expired, then it's not very useful to you. And so these are the two sides of the coin for why we need high-performance graph computing: the sheer size, the volume of data, and then the need to process that data very efficiently, very fast, so that you get your insights in time to exploit the insight. So where do we see graphs? Well, we have done a market survey, and we've looked at many different sectors, and some of those sectors are listed in this wheel over here. I'm going to touch on a few of them that we are currently involved in. At the top right of this wheel, you see intrusion detection, fraud detection, anti-money laundering. So these are all broadly what one could call security applications. We worked with BAE Systems to design a system for them for doing real-time intrusion detection in computer networks. The way they wanted it done was to build what are called interaction graphs. And I'll give you an idea of what those graphs are later. But given these interaction graphs, the problem was to find certain forbidden patterns within this graph. And if you find a forbidden pattern, then you alert a human operator because potentially a bad guy might have broken in. So this is something that shows up in a lot of these applications, like fraud detection and anti-money laundering. You basically have a very big graph, and then you're looking for certain patterns within this big graph. So it's the classic needle in a haystack problem. Another area where we are actively involved is in the identity management space. We have a customer who ultimately wants to go to a graph with 1 trillion edges. More classical areas that have been around, application areas that have been around for decades, electronic design automation. So these are the chip design guys like Cadence and Synopsys. Circuits can be looked at as graphs or hypergraphs in a very natural way. The pins of the circuit correspond to the nodes of the graph. The edges correspond to the wires. And you can take all of the tasks that they do in chip design, like placement, routing, static analysis, timing analysis, and so on, and do all of that using graph algorithms in parallel in a very natural way. The final area that I want to touch on is in the medical and pharma space. So things like precision medicine, drug discovery. So there are many diverse applications of graphs in these areas. This is one of our active areas of focus for Katana. So I'll talk more about it later in my talk, but to give you an idea of where they use graphs, a lot of these companies have what are called medical knowledge graphs. And so these are graphs that contain information about diseases, treatments, chemicals, papers that have been published in the medical area, authors, funding agencies, and so on. And what they want to do is to mine these graphs in order to find potential treatments for diseases, and equally importantly, to rule out certain potential treatments before having to go to the lab, do a lot of experiments, and then find that that potential treatment doesn't really work, which is a lot more expensive than if you could just do it on the computer. So there are many other applications of graphs, especially in this medical pharma space. I'll talk about some of them later, but this should give you an idea of the very diverse areas in which graph data shows up. So that brings us to Katana Graph. So we are architected to handle massive graphs. I'll show you a cartoon level block diagram of our system on the next slide, but at the heart of our system, we have a scale-out graph engine, which has been tested with some of the largest publicly available web crawl graphs, like WDC12, which has 128 billion edges. We have designed this graph engine from scratch for the needs of high-performance graph computing. And so as a result, our analytics are about 10 to 100 times faster than other solutions in this space. Most of our competition is focused on the graph database world. So there you have a lot of data sitting in secondary storage. You make a query, you want to serve that query fast. You do that by building lots of index structures and so on. So that is the kind of application that they're focused on, and not so much on analytics, which is the heart of our system. Of course, we're adding a database component to the Katana system, but at the heart, we have a carefully designed graph engine, which is how we get this 10 to 100 times speed up over other solutions. Massive scalability, we run on AWS, Azure, and Google Cloud. We have shown that the graph engine scales up to 256 machines on the Stampede cluster at the Texas Advanced Computing Center. And then what we do is support native AI and ML. We also interoperate with systems like PyTorch, so you can use those to complement everything that we offer. So if you do a slightly deeper dive into what our system looks like inside, I want to draw your attention to the middle of this slide where it says Scalable Distributed Graph Engine. So that's the heart of our system. And you see three modules there, Cusp, Galva, and Gluon. So Cusp is a streaming graph partitioner. If you have a large graph and you want to shard it across different machines, you can use Cusp. So you point Cusp to the graph that's sitting in secondary storage somewhere. So AWS has 3 buckets or Google Blob storage. And you say how many machines you want to shard this graph on. Cusp supports a whole lot of different partitioning policies, edge cuts, vertex cuts. You could also write your own if you like. So then Cusp springs into action. And then what it does is it shards the graph and builds an in-memory representation of each of those shards of the graph on the different machines of your cluster. Then the Galva graph compute engine kicks in. So each machine essentially has a view of a small portion of a graph. It thinks it has the whole graph, so it can just compute on it without worrying about any of the other machines. Now, Since you've sharded the graph, you do need to worry about what happens at the boundaries of the partitions or the shards. So you need some synchronization between machines to keep everything consistent. So the way we do it is we support what's called the BSP model. So you have alternating phases of compute and communicate. And so during the communication phase, that's where Gluon kicks in, and it makes sure that everything is synchronized properly at the boundaries of your shards and partitions. So that's the scalable distributed graph engine. Now, in order to make this into something real, you have to have high availability, resilience, fault tolerance, and so on. You have to wrap a lot of stuff around it. That's where my co-founder, Chris Rosbach, comes in. That's his area of expertise. He's giving a talk at this conference on what we are doing in that space. So I'm not going to talk about that. But let me talk a little bit about what we build on top of the scalable distributed graph engine. So we make this graph engine available to users through C++ as well as through Python. And what we have implemented are basically applications for graph query, analytics, graph mining, and graph AI. For graph query, we support OpenCipher, which is a very popular query language. There's a new standard GQL that's coming out soon, so that's on our roadmap. For analytics, we have a big library of the usual pathfinding routines between centrality, other centrality metrics, clustering, and so on. And then, of course, we are growing our graph AI library in collaboration with many of our customers. So this is the overall picture of what our platform looks like. So turning back to the title of my talk, I have told you about the need for high-performance computing in the graph space as we see it at Katana. Now let me address the other part of my title, which is knowledge graphs and graph AI. Now, knowledge graphs is a huge area. There are literally thousands of people working on it. There's a knowledge graph conference. There are many people, many different opinions as to exactly what constitutes a knowledge graph. People argue about ontologies and OWL and various things like that. But from the perspective of somebody like me, who comes from the systems and programming languages world, a knowledge graph really is just a heterogeneous graph. What does that mean? I'll explain that by contrasting it to what we can call homogeneous graphs. So if you take the Facebook friends graph, for example, the vertices represent users of Facebook, and if there are two people who are friends, then there's an edge between their vertices. And then you can mine this particular graph to find friends of friends and so on. So this is a homogeneous graph because the nodes are all of the same type, and then the edges are also of the same type. And typically in these kinds of homogeneous graphs, road networks, airline route maps, they're all examples of homogeneous graphs. There's not a whole lot of property data that's associated with nodes and edges. So in contrast, in heterogeneous graphs, and I'll show you a bunch of examples from pharma, financial services, and information security, the nodes have different types, and each type of node has different amounts of property data. Typically, you have a lot of property data. The edges themselves have types, typically, and then the edges may also have property data associated with them. So that's what I'm going to call knowledge graph. And we support what are known in the community as labeled property graphs. So here's an example from health and life sciences. So we were talking about these medical knowledge graphs. So the vertices in these medical knowledge graphs could represent diseases, proteins, genes, papers, authors, funding agencies, chemical compounds, and so on. And then you connect these nodes to each other depending upon the relationship between them. So for example, in this cartoon picture over here, there's a drug, and you can see there's a side effect. And if that drug has a particular side effect, then you connect the drug node to the side effect node with has a property edge. Similarly, if a molecule targets a particular protein, then you can have a different kind of an edge connecting the molecule to that protein. So this is what I mean by a heterogeneous graph. There are many different types of nodes and many different types of edges. One of the nice things about graphs is that they can represent entities at different levels of abstraction. So a molecule might be represented by a single node as far as these kinds of drug interactions go. But the molecule itself can be looked at as a graph. So that's basically if you look at it at the atomic level and you look at the chemical bonds between all of the atoms. So that itself is a graph, and that also can be represented within the same graph. And so this is one of the advantages that everybody talks about regarding graphical data. So graphs can represent entities at different levels of abstraction. And then the edges, by having heterogeneous edges, they help us capture complex biological relationships of different kinds, again, at different levels of abstraction if needed. And so ultimately, all of this information that is there in the graph helps you to train better models for things like drug hypothesis generation and precision medicine. These kinds of heterogeneous graphs are actually ubiquitous in applications. So we're working with one of the largest fintech companies in the world, and they have a lot of financial transaction data. So again, that can be represented very usefully as a graph. So you can see a node saying client over there. So there are a bunch of nodes, all of which represent the clients of this fintech company. And then a client may have a particular occupation. And so you see an edge going up in the diagram to an occupation node, and then the edge is labeled has occupation. The client may have purchased a particular service. Client owns an account. The account might be invested in a fund, and so on. So you take all of this information, all of this data about the customer, and then you can represent it very compactly and very nicely in this graphical form, a heterogeneous graph with property data on the nodes and edges. And then you can do things like payment fraud detection, identity theft detection, customer 360. So if you have a bunch of clients and you already know whether they're paying their mortgages or not, if you have a new customer who comes in, you basically can do a similarity check. So if this new customer's profile is similar to the profile of customers who are current on their mortgages, then perhaps you can approve that, and otherwise you don't. So you can use graphs and graph AI and graph machine learning in order to solve problems like that. And the final example of knowledge graphs that I'll show you, again, from a very different application area, is information security. So it's telling you about this work we did with BAE Systems. So there, what you're doing is basically recording events and resources as the people are using the computer network. I don't want to go through this graph in detail, but you can see there are a bunch of files, ports, IP addresses, processes, and so on. And then connecting the corresponding nodes, you have edges saying writes or reads or read and write and so on. And then given an evolving graph of this sort, there are certain forbidden patterns like the highlighted one shown in this picture. If you find that, then you're supposed to report that as a potential threat. And so a lot of security applications have this sort of nature. You have this big evolving graph, and then you're looking for certain forbidden patterns within them for doing intrusion detection. Identity management is another big application in this space. So that's the data, and now you need to process that data using what we call AI-augmented analytics. And typically what we find is you don't just want to apply one particular routine like Louvain clustering or betweenness centrality or whatever to your data. Rather, there's an entire pipeline that the data scientist wants to set up. And so everything from feature engineering, filtering, data cleaning, and so on, there are a lot of steps that have to happen. And what we want to do at Katana is to make all of those steps easy for the data scientist. Of course, we want to do this in a scale-out way because we also want to be able to handle massive training data sets. So to give you an idea of the kind of pipeline that we see with customers, here's something that we did for a pharma company. So what they're interested in is basically the following problem. They have a big medical knowledge graph, and then the task is described at the bottom right in the highlighted box. So extract oral drugs and associated targets for heart failure treatment, return the top 10 chemical compounds most similar to a given compound and their targets. So that's the English language description of the task. And the way that this is done is you generate what is called a graph pattern. So the graph pattern is shown at the bottom left. So this is a small pattern that you're trying to find within the host graph. So the host graph is that big medical knowledge graph. So there may be many instances of this particular pattern graph in the host graph. So each of them corresponds to a compound that's of potential interest. So the first step is simply to return that list of compounds. So every place in this knowledge graph where you got a hit. Then what you do is you execute what's called a chemical cartridge. So in this case, it's RD-KIT in order to compute the similarity with the molecule of interest. So in this case, benzene. There are many different similarity metrics. So they wanted to use something called Tanimoto similarity. So essentially you get a score now for every one of the compounds that you got a hit for. Then you rank them and then you return the top 10. And so what you see is basically you have to set up this entire pipeline over here. So you start by having this small query graph or pattern graph. You have to find all instances of it, collect all the hits, see what the compounds are, use RD-KIT, and then do the ranking and then output the result. This is just a small portion of the overall pipeline, but it gives you an idea of some of the complexities that one has to deal with when dealing with real problems. So in the last part of my talk, let me show you a few use cases that we have worked on. So the first one is in the area of unsupervised learning. So this is work that we are doing with this fintech company that I was telling you about. So they have a lot of financial transaction data. And what they gave us were two graphs. One is a small graph, so that has 100 million nodes and 19 billion edges. So we call that graph 1. And then the second one is the bigger graph, so 20 billion nodes, 44 billion edges. And again, the thing to keep in mind is that most of the storage is actually taken up by the property data that's associated with the nodes and edges, which I'm not showing over here. Now, they wanted to see what our analytics routines were like. And so what they wanted us to do was to compute some global graph properties. So in particular, PageRank and Louvain clustering. And I'm not going to go through the numbers over here. You can see what they are. But basically, we were able to do both PageRank and Louvain clustering in a fairly short amount of time, particularly compared to the results that we know of for Louvain clustering, for example. So in the open literature, the largest data set for which people seem to have done Louvain clustering is actually smaller than the small graph, graph 1, that we were able to deal with. So this gives you an idea of some of our analytics routines and the fact that we can do this in a scale-out way on 10 machines for the first graph. For the second one, we just used 80 machines. Here's another use case that we're working on with a customer. So this is molecular property prediction. The problem here is this: you're given a collection of molecules, such as the ones shown at the top left, and each molecule is labeled with certain properties. Now, these properties could be very different depending upon the task and the domain of interest. So for example, to keep things very simple, perhaps each compound is labeled with its toxicity, so whether it's toxic or not to human beings. And then the problem is, given a new molecule, you're supposed to predict, using all of the training data, predict the toxicity of this new molecule. Or if it's a different kind of property, so it could be quantum mechanical properties, then you're supposed to predict what those quantum mechanical properties are. So that's the problem. And this is a problem that people have tried to do in many different ways. One of our customers and our team came up with a different way of doing it, which we are entering into the TDC benchmark competition, which is one of the competitions in this area. So I'll give you a very high level view of how they do it. So what they did essentially was to take all of the training data, so molecules together with their labels, and they construct what they called a molecular similarity graph that's shown in the middle of this diagram. So in this graph, each of the nodes corresponds to a molecule, and then there's a lot of feature data that's associated with each of these molecules, including the user-defined features and then other features that our life science module determines is useful for this particular task. So given this graph, they then create embeddings for this graph using a GNN. And then given those embeddings and then given the test molecule, they make the prediction. So what we've done essentially is to take a problem where it was not obvious that there was any point to building a graph, but we were able to construct this molecular similarity graph and then solve the problem in a novel way by using graph technology. What's the advantage of doing it? Well, if you look at the current leaderboard for this TDC benchmark competition, so the task is toxicity prediction. The data set is what they call the HERG data set. So you can see the chart at the top. So the first three bars are the leaders at this point, and they use different techniques. The y-axis is accuracy, so higher is better. And what you see is that with the Katana GNN, you basically get a 6% improvement in the accuracy over the previous best. So the takeaway point here is that graphs show up in unexpected ways. This is a problem where it was not obvious that this had anything to do with graphs per se, but by looking at it in terms of graphs, we were able to come up with a new way of doing this prediction task, which is more accurate than what people have been able to do previously. The final application I want to talk about is a very exciting area. It's precision medicine. So this is an area that literally billions of dollars of VC money is going in. What's the problem of precision medicine? Basically, the problem is this. If you go to a doctor right now and you're diagnosed with some particular illness, you'll get some treatment, and chances are that treatment is the same as the treatment that would be given to somebody else who's also diagnosed with that disease. But obviously, if we could use a lot of data about you, like, for example, your medical records, right, and your genetic profile and everything that's known about you, we might be able to target the medicine more accurately. We might be able to do patient-specific treatment as opposed to something that's unaware of all of the details of your particular medical history. So there are many ways of doing this kind of precision medicine, lots and lots of companies. Recently, we did some work with our customer in this space, which again has to do with graphs. And here is how we do it. Basically, we reduce this problem to a graph classification problem. So how do we do that? The way to think about it is you're given training data. So you're given a bunch of patients, you're given a lot of history, medical information, genetic profiles, so lots of information about the patient. And then each patient is also labeled with whether there was a complete response, partial response, or no response for the treatment of interest. So that's the training data. What we do is we take all the information about the patient that we know and basically construct a graph that represents the data that's known about that patient. And then this graph now has the label for that patient. And then given a new patient, we construct the graph for that patient, and then we do a graph classification task to classify this new graph as, or to label it as complete response, partial response, or no response. So it's a graph classification task. In this area, they call it patient stratification. And this is essentially how we are solving this particular problem, again, by using graphs. One of the things that we had to do for this particular customer was we implemented a graph transformer network. We find GTNs to be very useful because you can also interpret the results very often easier than if you were just using GCNs. So we implemented a fast parallel GTN architecture, and the charts at the bottom of this figure on the right show you some of the results for our GTN implementation. So these are single machine Intel Xeon results. 3 data sets, ACM, BBLP, and IMDP. The sizes of a couple of the data sets are shown at the top. So let's just take DBLP. So it's a heterogeneous graph, which is what is important, as I was telling you. So nodes correspond to papers, authors, and conferences. There are 2 kinds of edges, so 2 kinds of relationships, paper author and paper conference. And then the task is a node classification task. You want to classify the author nodes by their research area. So that's basically the task that can be solved using GTNs. We started with a PyTorch implementation, and then it wasn't performant enough, so we implemented our own. And the charts at the bottom show you the training time, so it's a lot faster than the corresponding PyTorch implementation. And we get this faster training time without any loss of accuracy, as you can see in the charts on the right. So part of the secret sauce over here is that our guys came up with a new strategy for sampling paths in the GTN without losing accuracy. So let me wrap up now by giving you the big picture of what I've told you about. So we think big data analytics is a tremendous wave that's already here, and it's going to go even bigger in the future. Of course, analytics are not new. So descriptive analytics, here is what happened. So that is decades old. To give you an example from the medical world, it's a bit like saying, well, I had a shortness of breath and my chest was paining and there was this shooting pain going down my left arm. So that's descriptive analytics. It's a statement of, or a description of events that have happened. The next most sophisticated analytics is diagnostic analytics that tries to explain why something might have happened. So it's likely that you had a heart attack, and that would explain the symptoms that you have described. Even more sophisticated is prescriptive analytics. Not only is this the reason why you might have experienced those symptoms, but here are all the things that you need to do in the future in order to mitigate the bad effects of whatever it is that we think has happened to you. And of course, the ultimate Valhalla where we all want to be is predictive analytics. So here you take everything that's known about the world, about the patient, about the financial transaction, whatever it is, and then we want to predict as far as possible into the future by building all kinds of sophisticated models in order to explain what has happened in the past and to make predictions about the future. To do this effectively, you're going to need to process many different kinds of data, but we believe graph data is going to be an important part of this overall solution, and in particular, AI-augmented analytics of this kind of knowledge graphs is going to be extremely important. It's going to be a big part of the solution, and that is where we operate at Katana. With that, let me conclude. Thank you for your attention. It's been a pleasure.